In this video, we will consider one example of the PDF of the distance with origin or Euclidean norm for a non-circularly symmetrical random pair. In particular, we consider an important example of the joint distribution of a non-symmetrical, non-circularly symmetrical Gaussian distribution, and we want to find the distribution of R, the distribution of the distance. So for this example, like always, we could plot the delta dr, which is the outside of one circle of radius r, because this is defined by the region of all the points x and y which satisfy this one. This means outside of a circle with radius r, and this means inside a circle with radius of r plus dr. So if we integrate over the blue shaded area, we will find the PDF of r. So in other words, f r of r times dr is equal to integral of the joint PDF over blue area of f xy of x and y dx dy. So I have to put this expression inside this integral and try to find the result of the integral and put the boundaries of this integral. So we'll do that. Once we do that, you could, in that integral, you can change your dummy variables to polar coordinate and then simplify. Once you simplify, you obtain this integral, and this integral can be simplified a bit, but you'll reach another integral which cannot be further simplified. Let's see. So for that, you could simplify it to this form. Okay, so this is the simplest form you could get, and you have a constant a term which is a function of r, and also you have another function which is a function of r which cannot be simplified. This function in the honor of Bessel is defined as the modified Bessel function of zeroth order. So you can calculate it from a lookup table, and it is given that. So you see that if the pair x and y, they have the same variance, but the mean of one of them is non-zero, the distribution of their distance, because this is, let's say, the distribution of these, or envelope. Sometimes in communication system we call r equal to x2 plus y2 as envelope signal. This is in-phase signal. This is quadratic signals. In other application, we use other names for them. Or in power engineering, we call it RMS voltage, and this is the voltage, and this is imaginary voltage, but the complex numbers x plus j y is called phasor or whatever. Anyway, so if we plot this distribution for different values, because you have two parameters here, you have a parameter of mu, and you have a parameter of sigma 2. So if I put sigma to 1 and plot this function for different values of mu, so if mu is equal to 0, you get the Rayleigh distribution, which gives you these blue functions. And as you increase mu to 1/2 and so on, the center of distribution is pushed. So here, this is for mu 0, this is mu 1/2, this is for mu 1, and so on. So you see the center, the peak will be shifted over. As mu x increases, becomes large enough, this shape becomes more and more similar to a Gaussian distribution. It can be approximated by a Gaussian distribution. Obviously, a Gaussian distribution should go to -infinity, but this function is this value is only correct for r being positive and is equal to 0 for r being negative. So this distribution is known as Rice distribution.